Let me just introduce agenda today. Agenda is about first we will talk about a bit about CloudxLab, then a bit about a speaker, that's myself, and then we will do the introduction to machine learning, and then we will learn something like fundamental like gradient descent and backpropagation. Even if you are aware about these terms, please stay back in this session because I can assure you that you will learn a new way to look at gradient descent and backpropagation. All right. Then we will do the neural network and CNN. It's going to be a detailed understanding. I'm not going to do the maths here, but I can assure you that you will understand what it means by neural network and how does the backpropagation work. And then we'll talk about computer vision, and then we'll talk about generative adversarial networks, and then we will talk about face embedding, and we'll do a hands-on exercise with face embedding. All right, so what exactly is CloudxLab? CloudxLab is basically a platform whereby you can practice the problems, and it has the content as well. So it is basically one of the platforms like you have the Kaggle, you have Google Colab, and so on. CloudxLab is that kind of environment, along with the courses which is being done, some by me and some by other people. So a brief about me, those of you who already know me. I graduated from IIT Roorkee long back in 2002. That means around 17 years ago from now. And I worked in my career mostly on large-scale computing. I started my career with a company called D.E. Shaw. D.E. Shaw was the first place where I got exposed to the big data. We had the largest cluster known to the people. At that point of time, we had the largest cluster of 10,000 nodes in 2003. And then I founded a company called T-Bits Global, and using which most of the power plant of India are built. And then I joined in Mobi, where I was processing a data of 200 terabyte size and did the recommendation on that. And then worked with Amazon, the detail page. And I love explaining technologies, and I enjoy tinkering with tools and technologies. So I founded CloudxLab, and recently we have started a company called Deja Vu. The idea behind Deja Vu will be very clear to you because most of the technique that we're using there, today I'm going to demonstrate those. When we talk about computer vision, it's everywhere, everywhere. All right. So in every field, the computer vision can be applied, and it can improve. It can improve the human life in general. Whether it's biology, psychology, computer science, mathematics, engineering, and physics, in every vertical, there is a use of computer vision, right? As I was just explaining to you, the material science is not even included here. You can just say that it's included in physics. All right, so back to a simple question. What exactly is machine learning? What exactly is machine learning is the field of study that gives computer the ability to learn without being explicitly programmed. Yes? So this was by Arthur Samuel. He's written a wonderful, he's also considered as the father of machine learning in general. He has written, his book is really, really useful for many. All right, but I wouldn't recommend it to all of you. Instead, I'll recommend you something very practical soon. It's called Hands-On with Machine Learning and Deep Learning by Arlene. You can use that one. All right, so let's get started. And here, let's take an example to explain what exactly is machine learning. Even though these sentences would make sense to you, but trust me, the meaning of this sentence you can imbibe when you look at more examples. Yeah, so let's take a look at this example. What we have done here is basically taken up this video. It was done by Tom Murphy long back. What he has done was he had hooked the program to the computer. so that the program can play Mario by itself, learn by playing the Mario. So let's take a look at how it works. So in the beginning, when the program was playing, program is playing the keys and going nowhere. You can see the program is the one who is pressing the keys. All right, and observing the screen of the game. It goes nowhere, it dies of old age. Few weeks of learning from this game, it start learning a little better. It's about, it figured out by looking at the data, by looking at the images of the game, by looking at the screen, which is essentially lots of images, and it starts learning. Few more weeks into the game, now it is actually better than me. You can see that? It has got the intuition. You can see? So the program is learning by playing, just like you learned to play Mario by yourself. You see that? Do you think he'll cross? Yes. All right. So what you see is a computer playing Mario without knowing anything about the game. Only thing it knows is how to maximize the score. It's trying permutations, it's trying the machine learning to figure out what keys to press. What was that? What was that? Did you notice this? So when the Goomba is falling on it, instead of going down, it start going up. You see that? So what it did was, it figured out a bug in the game. It figured out that when the Goomba is falling, you start moving downwards, and that way you can stomp the Goomba. That we never knew. And what was that? No idea how did it do that. Now, when the same program was made to play the game, impossible games for it, like Tetris, it kept on pausing it. It kept on pausing it. And you know why it kept on pausing it? Because that was the safest thing to do to retain the score. It's exactly the way in the childhood, our cousins or siblings will spoil the game the moment they start losing it. So this is sort of an intelligence. So all of this is learned by the computer by itself, by playing game over and over, generating its own data and learning from this data to maximize the score. This is machine learning. This is the definition of machine learning. So if you have to make this program play Pac-Man instead of Mario, will you have to write new rules as per the game, or just hook it to the new game and let it play for a while? Yes, that's right. That's machine learning. The option one is what we used to do earlier. But today, if we have to solve this problem to play this game, we should, and we will probably go for option two. Now, that was machine learning. Machine learning is essentially learning from the data, making the computer learn from the data. Just like the way we learn is by the way of examples. To make you understand what it means by machine learning, I had to give you an example of machine learning that would help you, that you yourself now have figured out your definition of learning, right? Now, next thing that we talk about is what exactly is deep learning. The way nature inspired lots of innovations that you see. For example, we learn to make the plane by looking at the birds. Similarly, we learn to design the intelligence, taking inspiration from the animal brain. Neural networks. The animal brain is made up of lots of neurons. Each neuron is basically connected to other neurons, and the connections is what matters. And that's how the design of the computer program is. Okay, so basically we design the computer program to mimic the animal brain, and not exactly mimic, but inspired from the animal brain, that there are neurons, those are connected to another neurons, and there is an input on one side, there's a output on another, and so on. All right. So a big question probably lots of people ask me is, how does a machine learn? Probably this is more important question to lots of you, that we understand the definition, but question is, how exactly does the machine learn? Let's take a very fundamental, very basic question, and then we will see how we can understand it, okay? So be with me. Even if you are completely from non-technical background, I can ensure that you learn it, all right? So be with me, and this is not mathematical, this is essentially a general plain English, okay? All right, let's go for it, okay? So let's try to think about how can we make machine learn. All right, let's take the very, very basic question. Okay, so we learned that we have the data, we feed it to algorithm, and it gives the model. Model is the mind, right? The way we took the computer and let it play Mario for a while. It generated the data, it learned from the data, and it built the mental model, right? We take the data, we feed it to the algorithm. Algorithm learns from the data. Data is nothing but examples, like A for apple, B for bird, like that, right? C for cat, something like that. So we are giving example data that this is bad, this is good, this is bad, this is good. Both good and bad, as well as the photo that we are showing it, is examples, right? So we get the data, we feed it to the algorithm. Algorithm learns from it and generates something called model. And using that model, we take the real prediction, unseen data, and start predicting, right? So we learn from the data, and that learning is what we call the models. All right. Now, let's take a very simple example, like predicting the salaries based on number of years of experience. Yeah. So let's say your salary was 2,000 in the first year. Then in the second year, it was 4,000, then 6,000, 6,000, and then it'll be, yes, quickly. That's right. That's right. So question is, how can we make the computer do it? Good. How can we make the computer do it? It's extremely simple example of prediction. Extremely simple example of prediction whereby we are learning from the data. We learn from the data that first year the salary was this, second year it was this, third year it was this, and fourth year it was this, right? Thank you. So it's pretty simple, but we figured out in our mind, we have figured out that, yeah? It's 8,000, that was correct. Now, let's frame this problem for the machine, okay? So the parameter here is years of experience, 1, 2, and 3. The salary is the output, 2,000, 4,000, and 6,000. When we train, when we run an algorithm on it, the machine learning algorithm, it takes the data and generates the model, right? And then given the 4 as the input, it should give the salary as the output. This is an extremely simple example. So our algorithm should be capable of doing this, okay? Our algorithm should be capable of doing this. This is called linear regression, or you can say that we basically take a chart paper and draw the salary. So the way we make the computer do it is that take this data 1 year, draw it, take the another data, draw it, take the third data point, draw it, yeah? And then figure out a line that is going through it, yeah? So this line is the model, it's the mental model. Once we have this line, we don't need the older data points. We don't need to go to these 3 data points again once we have developed this line. This line is called the model. Line is represented by what all things? Yes? Slope and how far it cuts from the center. Yeah, how far it cuts the horizontal line from the center. Those 2 parameters are sufficient to define a line. A slope alone cannot define a line because there can be many lines that have the same slope, isn't it? Therefore, slope and distance from the center, it cuts the x-axis, there is another parameter. So now, can the computer come up with this line? Can the computer, looking at the data, come up with this line? Right? Answer is yes. We'll take a look at that. Once we have developed this line, we call this line as model. It's a very extremely simplistic case. In real life, this line could be a curve. In real life, this line could be, instead of only in 2 dimensions, it could be in 100 dimensions or 1000 dimensions or 10,000 dimensions. That's called a plane, hyperplane, right? So now, once we have this model, we can ask this model, hey, tell me the salary for 4th year. And how do you ask? By looking at this one. Just like we used to look at the log table, similarly, we're looking at this line. That when we draw the line from here, oh, this is the 4th year, how much is the salary? Okay, so computer can do good predictions given the data, right? It may not be able to give exactly same answer like 8,000. It might give you 7,995, or it might give you 8,100 or 8,050, right? Why? Because it's an approximation. The line may not be perfectly fitting. And that's also right, because in real life, the data is like this, right? In real life, the data is not perfected. Nobody gets exactly salary like this, right? Nobody gets salary like the way we took an example. The salary looks more like this, right? And we need to, the whole problem then turns into this. Can you figure out a line or a plane or a curve that can fit into these data points, right? Question is, how do we figure that out? How do we figure that out? The way we figure that out is by trying lots of lines, right? We try all these lines at line 1, line 2, we can try all kinds of slopes, right? And see which one is closest. How do we see the closest? How big are these intercepts? You see these lines? As per our model is saying that this should be salary, this should be salary, but actually this much. So our model is this much away. Similarly, our model is saying that this much salary, while this is the actual. So our model has this much error. Our model has this plus this plus this, or you can say a square of it. Okay, so so that's the error. So basically, we have to figure out all the lines. We have to figure out the best line out of all the lines that can be drawn, such that this difference from reality to the predicted is really, really small. I hope everybody is with me so far. Does it look really boring or really complex? So essentially, the problem boils down to this. Can't we figure out a curve, plane, or some line that goes through this data so that it can do the real prediction? Okay, and the first approach is this, that we draw these lines and try to figure out the outcome, right? Now, trying all possible lines will take, maybe a couple of days for even the computer, right? If you just keep on changing the slopes from 0 to say 180, and you keep on changing the distances for each of the slopes, if there are 1,000 slopes that you are taking and there are 1,000 intercept, like the point where the line cuts the horizontal line, this size, if you take the 1,000 such points, it'll become 1,000,000 such lines that need to be tried. So trying all possible lines is almost impossible. Therefore, we try a little greedy thing. We try a little greedy strategy instead of with the equanimity. We try all possible lines, thinking that the perfect line could be anywhere, and we do not worry about the time it takes to try it. Right? That's basically the simple strategy of permutation or brute force, we call it. The other strategy is we go a little greedy. There are many greedy algorithms. One of the greedy algorithms is gradient descent. Why we call it greedy is because whichever direction is giving you advantage, we start going that side. Okay? These class of algorithms are called greedy because they don't try everything. They try only those things that are giving them profit, right? Giving them advantage, that giving them the results, right? So they might get stuck in a local minima. They might get, they might get caught up, just like a pigeon gets caught up in the hunter's, trap. These greedy algorithms might get caught up there, but they generally do pretty good. All right. So gradient descent approach is like this. So we have a line, we increase the slope a little bit, and then observe, did my error increase or did the error decrease? Is it better fitting now or was it better fitting earlier? So we lift the slope a little bit, meaning we change the slope a little bit and observe the change in error with respect to the change in the slope. All right. If it is going really great, then we take a bigger step and draw another line. And now we start from the next line. We do the same thing again with the next line. All right. So it's basically, gauging the waters a little bit. I'll show you some more examples, then you'll get an idea. So basically, this is the formula. Don't worry about the formula. So how much to increase the slope is equal to some constant multiplied by rate of decrease in error with respect to change. Or you can say, we should increase the slope more if the rate of improvement is better. All right. If there is a better improvement, increase the slope more. If it's getting worse, then decrease the slope. Okay. So this is what is the idea. Really simple idea, but it gives great results. The idea of gradient descent has been really old and lots of people know it already. Okay. So this is how it looks like. All right. So new slope equals old slope plus some constant multiplied by the rate. All right. More the rate of change or more the improvements, bigger will be the newer slope. If lesser the rate or the negative rate, lesser the rate of change, the new slope will be bad. Question is, there won't be an ideal line. There won't be. Yes, but it will settle down after a while. Okay. So if, let's say, you were here, you increase the slope. The moment you increase the slope, this is the new line that you got, which is giving more error than it was giving earlier. Therefore, increasing the slope is a bad idea, and hence you decrease the slope this way. And by trying over and over this strategy, it will reach to the right line. Okay. So you start with the random line, increase the slope a little bit, and calculate the change in error. Did the error decrease? Yes, increase the slope. If the error did not increase, if the error increased, then decrease the slope. And stop if there is nothing happening. If that means you have reached to a point where you're just at the perfect spot. Either directions, you're going to make more losses, right? So at that point of time, you stop. All right. Now, a better way to think of this is this. You are in a new city and you're staying in a hotel, and there is one knob. You don't know which side is cold, which side is hot, and what good temperature would you like today. You don't have a thermometer, and you don't have a a way to directly set the temperature that, hey, I want exactly this temperature. No. In reality, what you do actually, you judge the water by touching it, right? And start twisting it, correct? That's exactly what gradient descent is. So look at this from this perspective. So this is the knob. You tilt it a little bit. You tilt it a little bit. Yeah. Check the water. If it has improved, move it more. Okay. And from the new position, you start again. Again, you try to improve, go to let's say turn it a little right. Is it going better or worse? And then you basically do that. In case in the first one, when you tilted it to the right, it started giving you the bad temperature, either too hot or too cold. Then you go to the new position, the other side. A question is, in the previous example that I took here, that we only thought about changing the slope, but in reality, we do both. We also try shifting this line a little bit, meaning the increasing the distance from the origin in the same way, exactly in the same way, the way we are changing the slope. The way we are changing the slope, we also try to shift it and check whether shifting is improving or making it worse, and do the same logic in case of the distance. All right. So idea is extremely simple, that you have the knob, you try to tilt a little bit, see if it's becoming worse or okay. If it's becoming worse, then go to the other side. Otherwise, you continue to this direction. Yeah. And you do this for all the parameters that are defining your model. In our case, there were two parameters that were defining the model. One was the slope, and other was the distance from the origin on where the line cuts the horizontal line. Both of them, we do the same logic the way we are tweaking the knob. Yeah, I hope this example is clear to all, that we are tweaking the knob in order to get the best water, right? The best could be warm, best could be cold. We don't know what is your definition of best. Therefore, you try and you optimize on the rotation. Perfect. Now, what if we have two knobs? Let's say one knob represents the flow, or let's say one knob represents the flow of hot water, other one represents the cold water. The question is that how would you handle this case, right? So what you do in general is, in case of like machine learning, is that you apply the same strategy as gradient descent. The only difference is you do one knob at a time. Yeah, you do only one knob at a time. So in reality, there could be hundreds of such knobs. These are called parameters that we need to tweak. Instead of you tweaking it, computer will tweak these parameters in order to get the best results. The way you tweak the way you were tweaking these knobs in order to get the best comfortable temperature of the water. Similarly, computer will be tweaking these hundreds of knobs or thousands or millions of knobs in order to get the best water. And it'll apply it, right? Let's say looking for good flow as well as good temperature, right temperature and good flow. So you will try hot and cold, both turning both these knobs. In reality, let's say in reality, if you have to build a system whereby looking at a person's gender, country, given the temperature of hot and the cold and the climate, if we have to get the best for each gender from each country, then probably we have to train a model with many knobs so that it can give good flow and good temperature, right? And we'll need more such knobs. These knobs essentially represent the slope and the other parts of the example in case of linear regression, right? These are called the weights. All right. So what I have trying to bridge the gap is, I'm trying to bridge the gap between the linear regression. I'm trying to bridge the gap between linear regression, neural network, and the gradient descent. All right. All three are same thing. You will get a very clear understanding. All right. So be with me and do not lose the interest that, hey, it's too technical. I can assure you that none of these examples are technical, and I've experimented with many users from different backgrounds, and they have been able to learn these parts. All right. Now, in case of artificial neural network, we have lots of neurons. Okay, and the lots of neurons is basically like this. This is the input layer. Okay, this is the output layer, and these are called neurons. All right, and these, you see these connections? These connections are the ones that will look like knobs to us. The way we were tweaking the knobs, a neural network will either cut these connections or will make them strong and so on. So this is the input layer. Let's say this is hot, cold, gender, country, and so on. And this is right temperature, right flow, and something else, right? And these are, you know, the internal neurons. Okay. On the right hand side, you have multiple layers of neural network. This one is generally we refer to as a very shallow network or simple neural network, or sometimes we also call it perceptron. And this one is called deep learning neural network, or you can say deep neural network, DNN. Okay. So the way we represent a neural network, let me explain again. The way we represent a neural network is like this. There are inputs, yeah. There are inputs like this is the first pixel of an image, second pixel of an image, third pixel, and so on. So we have the input image here. Output is whether it's a cow, it's a buffalo, it's a dog, or a cat. Okay, these are the four things, let's say, we have to represent. So everywhere it is going to be like this. This is the input layer, this is the output layer, this is the layer of neurons. Layer of neurons do nothing but take the input from all of these, multiply by certain number, and give out, and then add some number and give it out. That's what a neural network, that each neuron do. Each neuron is connected to all the inputs and so on. Similarly here, you have lots of neurons. These are conceptual ideas, basically a software, a program, whereby we say that, okay, I need 4 layers of neurons, with each layer having these many neurons. They get connected to the input one. So if this is the input, it'll basically multiply with, it'll basically multiply all these values with the connection strength. Okay, I'm going to go more detail, don't worry. So basically, this is how the connections are built. This connection represent the stronger connection means this number is really, really big. No connection means the number is 0. I'm going to go into more detail. So conceptually, this is how you can think of a neural network. This side is called input layer. This is called output layer. And these are neurons. Each neuron is connected to every neuron in the next layer. This one is connected to all of these, this one is connected to all of these, and so on. These are multiple layers. This is the first layer, this is the first neural network layer, the second, third, and fourth. This layer just is a hypothetical layer. This is basically representing the input that we are giving it, right? The way your eyes are giving the sensors to your brain. Similarly, this is going to be a pixel of a photo, second pixel, and so on. And this one is the result, like whether it's a cow, or it's a buffalo, or it's something else. So that is the way of thinking about neural network. Now, going back to the example that we took earlier, if conceptually we have this data about climate, gender, country, and the hot temperature and cold temperature. And also we know how much is the good flow and right temperature for them. So coming up with the relationship between this input and this output is what we call the machine learning. Coming up with a relationship between inputs and outputs, looking at the data, is what we call machine learning. The way it works is that we have weights, these knobs, remember? These knobs, we keep on adding, right? So people discovered that if we add more and more knobs, it can actually solve really hard problems. Okay, if you add more and more knobs, it can figure out better relationships. Okay, so this is kind of neural network, deep neural network. Please keep in mind that this knob does not represent the neuron. It represents the connection between the neuron. Okay, this is called a neuron. This is called a connection. Okay, so here knobs represent the connections. All right. So what we are doing here is, if we keep on adding more and more knobs, we will be able to build really complex system. For example, if we have to identify that this drawing is about 8, right? This drawing is about 8 or 4. We'll feed this to the neural network such that one pixel becomes an input here, second pixel here, and so on. If there are, this image is of 28 by 28 pixels, then the total pixels that we are entering is 784 numbers, right? So we're feeding 784 numbers here. These are the connection weights, okay? These are the connections, and this is the neurons, right? And here are the output. We're expecting that if it's images like this value should be highest, while this value should be, all of these should be 0, okay? So what we do is we basically let the system predict the probabilities, and then what we do is we train these layers, just like the way we train our, the way we twisted the knob in order to meet our temperature. Similarly, we are going to twist these connections. Connections are what we call knobs here. We are going to basically try making this connection stronger, and see whether the result is coming closer to what we are expecting, right? And that way we would be able to come up with a machine learning model or deep learning model which can predict what is there in the image. So essentially what we do is, the way we do is, first we go with a forward pass. We take the image, let these weights be random, just like we started taking bath, let the position of the knob should be anywhere. Similarly, let these connections be random in the beginning, right? And based on these connections, we multiply those numbers with the input, we get some result, then we again have some more random numbers, we get some random results. Now, okay, so in the forward pass, we calculate it, we get some values here. This is the computed, and we are expecting that it should say 1 in case of 8, right? So what we do in this case is that we calculate how much is the error. Even though all of these were random, we are calculating how much is the error. Now, what we do is we tweak these knobs. These are the knobs. These connections are the knobs. We tweak these ones and observe whether increasing this, did it increase the error or did it decrease it? Accordingly, we start manipulating these connections. If, let's say, cutting this is giving us better results, so we cut it. So it's not you who is going to do it, but it's the computer that's going to do it. It's going to try increasing, decreasing these connection weights to see whether the error is going up or down. All right, so it's going to tweak these knobs in order to reach to the actual work. Okay, and that's how it is going to do. So it's going to try with 8, then it's going to try with O, and do the training over and over, and we do it with lots of examples. So this way, at the end of it, it'll come up with those position of the knobs which can convert this image into the actual number. All right, we'll feed it 8, tweak the knobs. We will feed it 4, tweak the knobs. We'll feed it with the drawing of 1, drawing of 2, drawing of 3, and then to keep on tweaking the knobs. And at the end of it, the system will learn how to predict just by tweaking the knobs. And these connections are nothing but knobs. All right, now another example that you can think of is, given the photo of a person, can it predict whether it's a male or a female? Yeah. And for that, basically we just need to feed the photo, tweak the knobs, and see, compare the outcome with the actual results, then tweak the knobs and keep on comparing and then keep on tweaking. Okay, after a while it will learn the position of the knobs. That position of the knob is what we call the model. There is one question that has come twice, so let me answer this. Question is, deep learning and artificial intelligence are same or different? All right, so okay, there is machine learning, there is deep learning, there is artificial intelligence. So one thing I have not defined is artificial intelligence. Artificial intelligence is about building artificial intelligent being. Okay, something that behaves like people, something that behaves like human. That is artificial intelligence, right? Artificial intelligence is not a technology. Instead, it is the objective that can we achieve AI. Earlier, we tried to achieve AI by writing rules in programming, by creating our own logic and so on. That did not work out. But now, while letting the machine figure out the rules, while letting the computers look at the data and come up with these rules, the position of the knobs by itself is something that's going to work out, and that is working out because that's giving great results. So deep learning and artificial intelligence are two different things. Artificial intelligence is objective, while deep learning and machine learning is a technique, or you can say a suite of tools, or you can say the science or maths behind it. All right, so I hope you're clear. Machine learning is the general suite of tools. Deep learning is one branch of machine learning. Okay, now coming back to it, so we discussed that we can tweak the knobs, and come up with the position of the knobs that can predict really complex things like images. What is there in the image? Is it a digit 1 or 2? But just by tweaking these knobs. All right, knobs here represent the connection strength between neurons, these lines. Okay, so which one to draw, which one to delete, which one to make stronger, which one to make lighter, let that knob decide. Okay, so we basically tweak the knob to achieve the result. Tweak the knob to achieve the result. Okay, now the challenge is that when we are taking each pixel out and making it in the straight line, the relationship between the points because of the position is actually getting lost, right? This is the first pixel, this is the second pixel, and so on, right? So CNNs solve it by cutting the picture into smaller pictures and then applying some kind of filters on each portion. So it basically cuts the whole image into smaller parts and then combine that and feed it to the neuron. Okay, so this is how it looks like. So it looks at the photo, and this is basically a two-dimensional way of looking at the neurons. So this is basically a little advanced structure of the neural network called convolution neural network. So convolution neural network, I'm going to skip this part because this is just too much for this session. So a usual neural network, a usual model, it comprises of many types of neural layers, right? This one is convolution, whereby it's cutting the big photo into smaller chunks and converting it into numbers. And then this one is summing up all the values, then again doing the convolution. Convolution is basically cutting it down into smaller portions and then acting upon it. Then the normal knobs, the one that we discussed, and then the output. So this is a big model. Okay, in practical, in reality, this is how the model looks like. Okay, so basically the computer vision is about this: a huge complex neural network, the artificial neural network, having millions and millions of knobs or connections, and giving the output that we're desiring. And how it is tested, let me just give you a good example. So there is a image classification challenge. This challenge is called ImageNet. It has been going for many years. The challenge is to classify 1,000 objects. There are total 1,000 classes, though there are 1.5 million pictures. Given a picture, we have to tell which of the 1,000 object is there in the photo, whether it's leopard, is it a motor scooter, or is it a container ship, or is it a mite. So given these photos, it is supposed to predict what is there in the photo. There could be multiple objects, like in the third one, there are people in the photo, so it is supposed to predict those. In the third one, there is a motor car in the photo as well. So basically, giving these 1.5 million images along with their labels, the labels are of 1,000 kinds. Okay, every image is marked with the name, whether it's leopard, motor scooter, container ship, mite, or there are person, a kid, and dog, and cat, and horse, and so on. There are 1,000 such classes, 1,000 kinds of objects. So this data set of 1.5 million images actually has all of these tags. And this is something that is amazing about this database. It has really, really detailed images. All right, using this ImageNet, we have been measuring the performance of the machine learning models. ImageNet is basically a big data set which has already labeled images. Okay, I hope everybody is clear about what is labeled. Now, this is the progress as recorded over years. In 2002, the error rate was 28.2. The way we are measuring the performance is by measuring the error rate. And the error rate has been, in 2010, it was 28.2. You can see that. Then in 2011, it improved a bit, 25.8. Then in 2012, LXNet came into play and the error dropped down to 16.4. Then 2013, the error rate dropped down to 11. Now in 2014 and 2014, you can see the error rate dropped down to 6.7. Now, the amazing part to know is that humans' error rate is 5.1. 5.1 is the human's error rate, while in 2015, when ResNet came into play, these are the various structures of the neural network that people came up with. In 2015 was a big invention that happened. The ResNet basically overtook human. Human does 5.1% of error. It's not really percent. I'll come back to that later. So humans' error rate is 5.1, while computer's error rate dropped down to 3.6. As of 2017, the error rate has dropped down to 2.3. After 2017, there have been slight improvement, but nothing considerable, while the efficiency or performance of prediction has gone really down. So you can see that we are talking about reality. It's not something hypothetical. the error rate in predicting the object classes in given a photo is has dropped down to 2.3, which is way twice better than human. Okay, this is an amazing part. So machine learning is about learning from data. So computers learn from this data, which is labeled 1.5 million images labeled with 1,000 objects, and it has started predicting giving unknown images. If you give it something random which it has not seen, still it'll give very good results. Okay. Now, with this in mind, the AI looks reality. Okay, AI looks reality, and it is way better than people in many cases. Way better than people in many cases. The only difference is, in case of humans, we are so efficient that by looking at a couple of images, we learn about most of the objects, right? The kid learns to identify so many objects by looking at maybe thousands of images, right? But in case of computers, we had to feed it 1.5 million images, and it took a long time and lots of computers to do it. All right. Now, there are many more computer vision related problems, such as object detection. One of the common problems is the object detection, action classification, image captioning, for example, like there is a person, there is a hammer, there is a nail, and there is a person on the bike, and so on. Figuring out what's going on in the photo is also part of computer vision. It's not only identifying what's there in the images, but also figuring out the intent. Okay, if there are multiple things in the photo, it is supposed to identify those, right? A typical CNN is like this: given a photo, we feed it on one side, and it on the other side it gives the score that I think 90% chance it's a cat, 5% chance is the dog, 1% chance it's a car, and so on. So it gives you those scores, right? Those scores, and that's where the magic is happening. Given a photo, this is a typical CNN. This is what we do. There are many kinds of CNN that I walked you through, ResNet and all of those. They're essentially convolution neural network, whereby it's cutting the bigger image into smaller pieces, into smaller rectangles, and converting each rectangles into some number, feeding it to the neural network, and then operating on it, learning from this, tweaking the knobs in order to achieve the correct probabilities. Okay, so there are many kind of computer vision tasks. One is called semantic segmentation, whereby in the photo we are supposed to fill it with dots, marking exact boundary of object, like different, like you can see there are different colors for grass, for cat, for tree, for sky. So those pixels we need to identify. This is called semantic segmentation. The second kind of problem that we solve in computer vision is called classification and localization. Okay, so classification or localization is essentially trying to draw a rectangle around the object, figuring out where is the cat, where is that rectangle surrounding the cat in this photo. The third thing is object detection, whereby there are multiple classification or multiple localization. Instance segmentation is essentially if you have multiple objects and you have to identify the dot cloud, we call it point cloud, in order to mark the boundary of every object. These are the various computer vision tasks. The way AI works is that it cuts it into portions, check it with the neural network, whether this portion has the cow or not. Let the system predict whether it's a cow or a grass. So you can see that it has, this one has grass, this one predicted as grass, this one predicted as cow, this one predicted cow. So the way it works is that it slices the whole image into these overlapping rectangles, and then let the neural network, which has been trained to predict the objects like cow, grass, and so on, it predicts the particular object, and then we overlap it. We overlap it, and we basically overlap those rectangles to form the object. Okay, to form the rectangle surrounding the object. So this is essentially how AI works in it, or you can say machine learning works in it. Okay, there have been many algorithms to do the object detection, or you can say draw the border around the object. Given a photo, not only identify whether there is cow or cat in the photo, but also identify where is that cat found. Draw all the rectangles on all the objects in the photo. For that, we use these algorithms. The one that is most popular is YOLO V3. And basically, the way it works is it overlaps the rectangles. Let's take a look at the algorithm YOLO V3. It basically works really well. Okay. Can you see? So this is how it's identifying. So it takes every portion of the photo, feeds it to the neural network, and checks whether it's a person, cow, or a dog, and then merges such small photos together to make the full boundary of the object. Yeah. Here, it doesn't know what's an eagle, therefore it's completely confused. It's thinking it's a dog, and so on, right? So it's doing it almost real time. It's really, really good. You can see that? So you can see that once we have solved the problem of identifying people in the photo, we can do driverless cars, we can do so many magical things. Okay? We can do so many magical things. See that? All right, so you can see that there is a person in the photo, and the amazing part I'm going to show you is this. So sometimes it's tagging it like a bird, sometimes it's tagging it like a dog. All right, so moving ahead, so this is how YOLO V3 performs. Okay, so one of the things that I built, you can take a look at this particular blog post whereby the camera was chasing the person on the stage. Okay, so essentially what it was doing is it was identifying the person in the photo and then rotating the camera to focus on the person. We call it AI cameraman. The post is here public in case you want to build it. The code is also there in case you want to try it out. Okay, I'm posting it to all of you on the chat. You can take a look. So the way it worked is that there is a computer which has a webcam. Webcam takes a photo, computer processes the photo and identifies if there is a person. Is it is the person touching the upper border or so? So if the person is here, identifying where is the person on the left or person on the right. In case person is on the left, then it sends the signal to this microcontroller, which sends rotates the motors. These are the motors, and these motors rotate the camera. Okay, this webcam is sitting on the motors. Okay, and the power supply connects these motors. All right, so the way this is how it works. There are many more use cases I'm going to talk about. In case you want to build it, and if you are facing challenge following this one, just reach out to us. I'll try my best to help you out, or come over to the discussion forum, the one that we have on our website. I would love to help you in this. I've open sourced it, and if you want the hardware specifications, exact specification of every component, I can give you that. Okay. So it's an auto cameraman whereby it focuses on the person on the stage, just like instead of having like a person dedicated on focusing camera on my face all the time as I'm speaking on a conference, I basically can use these. Okay, if this one is a free post, everything is open here, and so on. All right, now there's a lot of magic possible by combining the natural language processing and computer vision. And that is the thing in the human intelligence. Looking at the photo, understanding the context, and then operating on it. That is the magic that is going on right now. Here you can see that man wearing a black shirt and elephant is standing and so on. So it's very, very, very important to understand that computer vision can lead to an enormous amount of intelligence, enormous amount of AI. I mean, we can achieve AI with these computer vision techniques using machine learning. Okay. Now, there is one quick thing that people ask is what exactly is generative adversarial network. I'm going to show you something amazing right now, and then I'll just move ahead very quickly. So this is one thing that got the Nobel Prize. Okay, basically it's the most amazing thing that happened. So what they did was they took two neural network, one that can detect whether there is a person or not a person, right? In the photo, is it a real person or not a real person? So that's basically a detector. The way we just showed you that is detecting whether there's a person or not. That's a part here. And then they created another neural network which will take the noise, generate some random stuff, and give it to the detector and ask, is it real or fake? If it's fake, then it start tweaking it. Then again ask the detector, hey, is it fake now? It says, no, it's real now. Then it learns, the generator learns to generate faces thanks to the detector. So these are two neural networks like police and the thief. While police is trying to catch the thief, thief is coming up with new technique every day so that the police cannot catch it. All right. So using this kind of neural network against neural network kind of a model, amazing things happened. Okay. The computer learned to create faces. It learned to create faces from random noise. And basically the way it works is take the random noise, tweak the knobs, create some output. Then feed it to the discriminator and then compare whether it's a real or not. And that way, this one is learning how to create the faces. Now let's take a quick look here. So all the images in this are automatically created. Okay, I'm going to show you this. You can see all the photos that you see here are automatically created. I'm going to pause it a bit. So if you combine this face with this face, this is what you get. If you combine this face with this face, this is what you get. Combine this with this, this is what you get. All right. So you can see that this is amazing. This is amazing in the sense that you have multiple use cases of AI. It's like artists painting people, new people that you have never seen by combining existing knowledge about creating people, creating photos of people. All right. So this is just, amazing. So I'm going to walk ahead. You should take a look at this link that I'm posting on the chat, and it's just amazing. You would not like to miss it. Okay, so it's basically can create faces. All these faces that you see are automatically created by the deep learning technique that we have discussed today. Okay, so you can see You see that? All right, now let's get back to the hands-on exercise. Okay, so one of the technique that came out of all of this is converting a face into numbers. So a neural network was trained on lots of faces, and the objective was this: given a face, come up with 100 numbers so that it can give some good results. Okay, we call these numbers as embedding. So a neural network or a machine learning model can convert a face into these numbers. The great part is this, that if this photo is of the same person, even at the different age, even wearing a different cap, wearing glasses, having beard, mustaches, these numbers are very close to the original one. Okay, at the different age, different kind of beard, different glasses, different different hat, different shirt. Even then, these numbers, these face embeddings are very close to the original one. All right, let's take a look at this really good hands-on. I'm going to talk about it now. So what I did was I did a very simple thing. That's me. And what I did was I converted my face into the numbers. We call that face embedding, right? Using a neural network. Neural network came up with these numbers. Similarly, I downloaded 1,000 images from IMDb of all the celebrities, top 1,000 celebrities, and then converted their faces into these numbers, okay, into the embedding. All right, I hope everybody is okay. So these numbers do not represent something tangible. It's very hard to interpret these numbers. These numbers are generated by a neural network. And the way the neural network was designed is come up with these numbers such that same person should have similar numbers, while the different persons should have different numbers. Okay, that's how the neural network was trained and the face embedding was generated. Okay, so I'm going to show you how to do this. First of all, we converted every face into these numbers, and then I computed the distance from it, and then picked the one that looks closer to me. This guy, this Suraj Sharma, I have never known this actor. He actually looks like me when I was younger, like 20-year-old, 25 or maybe. Okay, so it's really amazing. I never realized that this would work so well. So my suggestion to all of you is give it a shot and share your photos with me. Okay, so or with CloudxLab on Twitter or Instagram, wherever you want. Okay, so let's just go over this hands-on example. Let's get started. If you already have CloudxLab subscription, then it's good. Otherwise, you can also set up at your own one. So the Git repository that I created is available here. Let me also give you the link. All right. If you click on CloudxLab, you see lookalike celeb. Okay. If you want to be contributor to this, just let me know. Okay, so what we have is one piece of code. This is a piece of code that downloads the images from IMDb. This is where I've downloaded it. So it's a crawling code. I wrote the crawler, which basically parses the HTML and downloads the images. And once the images are downloaded, I have these. I actually downloaded the images, so you don't need to worry. These are the images of various actors. Okay. All right. And you can see that these are the various actors. Okay, the more the images, the better it's going to be. So if you have a better way of crawling IMDb, feel free to do so. It's not going to be too hard. Okay, now this is the notebook that you see, find similar actors, right? This is the one that I'm going to show. Okay, and I've already cloned this repository locally. You can also clone it if you have not cloned. Okay, I'm going to use my CloudxLab account. You're free to use your own local machine, but setting up OpenCV and setting up these libraries is a little harder. Therefore, if you do not want to buy CloudxLab subscription, you can just take a 7 days trial and then try out this example. All right. So here, this is my home directory. If you have installed Jupyter locally, you will also see this in the same way. And do you see lookalike celeb anywhere? Lookalike celeb? No. All right. Is it like? Okay, never mind. So I'll just open a console terminal, clone this repository. Okay, I'll just take this. Okay, don't panic if you're not comfortable with this terminal, because just get comfortable using terminal and the Python. My suggestion will be just take up our free Linux course. That'll help you out a lot in make yourself comfortable. If you're planning a career in machine learning, AI, deep learning, or any kind of programming, using a terminal is mandatory. Okay. So I'm just cloning this repository. Oh, I already have. Okay, so if you have not known this, you can just go to the terminal, type this particular command, git space clone, and copy paste this URL that is popped here. Okay, now I have already have the folder here, you can see, and I'm wondering how come Jupyter doesn't show me. It should show me, right? Lookalike, last modified, no. Okay, let me again sort it. This is 8 days ago. And do you see lookalike? Yes, there is a folder here. All right. So you can see that this is the notebook. Right now, I'm opening the notebook in CloudxLab after I have cloned the repository. Once you clone the repository, this folder will appear in your home drive inside Jupyter. When you open the Jupyter, you can just go to, okay, one way would be go to my lab, click on Jupyter. Okay, first go to the terminal, go to my lab, click on Jupyter, go to the terminal, do the git clone. Okay, and then come back to the Jupyter interface, which will look like this, and click on find similar actor. Okay, and there you will find this notebook. Okay, now so here it's loading all the libraries, then it's loading all the images. Now notice this part. What we are doing is we're going to go through this known images directory, convert each image into embedding, and then each image into embedding here, and then keep those embedding. Okay, so here we go. And after that, we're defining a function to calculate the difference between one face and another face by comparing the face embedding. And once we've done that, let's get started. So here I have loaded the images. Okay, I have loaded the images, and you can take a look at my image sandeep.jpg. After that, we calculated the face embedding. Okay, all right, it is going to take time because loading the, so right now I'm just calculating the original image, sandeep.jpg's distance, and then finding the matching image. Okay, it's going to take a bit of time, but only for the first time. All right. Okay, I've just taken the images of various people from my LinkedIn network and try to apply the same logic here. Or did it work? It's working. Let's just hope that it finishes. Okay, it says original image not found. Did I miss something? Yes, I missed this part. I'll run it again, and then I run it again. So you can see for this person, the image, the matching image is this, right? If you want, I can just take a look at your LinkedIn image. You can post a link to your image. I can try demonstrating with your image. Okay. All right. So I tried with multiple people here and try to see for this person, this actor is matching. Okay. This actor, this actor is matching for, okay. All right. So all you got to do is here, just go to again Jupyter Notebook. Here, these are the various photos. This is mine, then these are my friends' photos. You can upload a new photo. Let's say, give me a link to image. Anybody? Okay, we have Roshan Pandey. Okay, Roshan, let me just give it a try to your photo. Okay, let's try to find who is your lookalike actor. Okay, let's just pick his image. Open image in new tab. Good. Let me just save this image. Okay, I'm just saving it to download, and it's called, let's call it Roshan, right? Roshan. Okay, now once we have downloaded this image, what we can do is simply click on upload. Okay, and select the image, upload the image, right? And click upload again. Don't forget this part. Now we are here, and let's try it out. Okay, so this time original image is Roshan, and then this is going to be the matching image. Okay, let's call it ROSHN. This is the original image. Let's find out the matching image. Okay, so you look like Bruce Lee. Okay, so you guys should try it out. It's actually pretty straightforward. You just need to run this piece of code from here to here, and then you can try it out. Okay. Okay. Copy link. I'll try it out. It'll be super fun. I'm going to build this simple LinkedIn thing whereby it'll just say the name of my friend's contact. Okay. So let me just save the image for, let's say, Nirmal. Okay. And then upload this image to my CloudxLab account. This folder, Nirmal, here, I've selected and clicked on the upload, and then went back to my notebook and copy pasted these 2 lines. Okay, I will add these 2 lines. First, it's nirmal.jpg, right? Correct. So I have loaded the image correctly. There is no problem. Now it's saying that calculate the phase distance of this original image and find the matching image. Okay, it look like this particular actor. Let's just say, see the name of the person. It's John Kegel. Okay. All right. So give it a shot, and yeah, you will find a celebrity who looks like you. I hope, Roshan, you are not disappointed. You are the Bruce Lee and the Bruce Lee. Okay. Yeah. Let me just see the name also. I should print the name also. Right. The name is the matching image. Yes, Bruce Lee. Okay, so I would suggest all of you to post your lookalike actor, and then on maybe Twitter, tag CloudxLab, and it'll be fun to do that. That way, we will actually all at least try to learn how to do it. Okay, perfect. A question from Akash is, we can duplicate our profile images to CloudxLab and run it there. Yeah, that you can do. That's what I've done. I've basically downloaded to my local machine and then uploaded to my CloudxLab account. But what you're suggesting is duplicate. That would be even way more easier. Yeah. AI means artificial intelligence, which means that anything that looks like human or behaves like human intelligence, we call it intelligent. Okay, so artificial intelligence is objective is to build things that can behave like human, think like human, and that is the artificial intelligence. Artificial intelligence is the purpose. It's not tool, it's a purpose. It's a purpose. Even if you are coding, you are writing rules and making things behave like human, that's also counted as AI, right? While machine learning is different. Machine learning is set of techniques whereby we learn from data. So usually, let's say you're building an artificially intelligent camera, the one that I showed you, right? The AI cameraman, the diagram that I showed you, it'll comprise of two kind of things. One, human coded, people have written code. And second, it might have the machine learning angle. So for AI perspective, it doesn't matter whether we are using machine learning or rule-based approach. From AI perspective, the end objectives should be met, that it should behave like human. Okay, behave like, and it should be intelligent like animal or human. So that's essentially the AI. Machine learning techniques, there are many machine learning techniques that are used which are beyond AI. There are machine learning techniques which was basically, machine learning was initially, invented to meet AI requirements. Okay, basically machine learning is a kind of a field that was designed so that it can come up with the intelligence at its own, looking at the data. So machine learning is a field of the computer science in which we study the techniques, algorithms, tools that learn from the data and make it learn from the data. Deep learning is a subfield of machine learning which deals with neural network, the computer programs inspired from the animal brains. Right? Now, coming back to the question. So this question is, can we train a model to exact handwritten characters from a document using computer vision? Yes. Okay, can we extract? Can we train a model? Yes, of course. OCR is all about that. Okay. A question from someone is that if students learn computer vision technologies, which company they are suitable for? Please give the list of companies. Today, almost every company is asking questions. I never knew this part actually. Some of my students wrote on LinkedIn or sent me an email saying that, hey, even though I was a student, I learned your course, but it actually helped them in their 4th year in the campus placement to get a better job. And those students did not only get a job at the campus, but their salary was way different, even though that was not announced. Okay, so this was a surprise to me earlier, couple of years ago. I was thinking that it may not be useful for students, but it turns out that every company is focusing on hiring students who have good knowledge about programming, good knowledge about building systems and building machine learning. Okay, so you definitely get an edge over the other students. I hope that answers your question. Question from Samuel is, what is deep learning? Deep learning is a branch or part of machine learning. Machine learning has many kinds of algorithms. Some are based on, say, statistics. Some are based on decision trees. Some are based on, say, linear regression, the mathematical formula of SVM. But there are some algorithms that are inspired from animal brain that is called, those branch of machine learning is basically deep learning. How to make predictions on a new class of image? That's a question from Praveen. How to make predictions on new class of image such as new type router? considering it never existing before. Here router is just use an example. Yes. So what you can do is you can take up existing neural network model. It's available publicly. You can add one more class, modify the neural network a bit, and then get lots of images from the internet representing router, and then retrain the neural network to predict the router. All right. So this is basically what we call is very nice thing. It's basically we call it the pre-training, utilizing the pre-training. All right. A question from Rashmi is, I had one question. If you are in lift and tell, hey, move to third floor, is it deep learning or machine learning or artificial intelligence? Voice recognition comes under which process? Good question and very hard one. I'll try to answer this. Please focus, everybody. This is going to be quite useful to you. Let me. So voice recognition earlier was based on rules. People coded the rules that if the amplitude is this much, followed by this amplitude, then followed by that, it means A, otherwise B or C, and so on. So before machine learning, we hand-coded these rules. We call all of that came under voice processing, and which is under signal processing. But today, those all branches have become machine learning because they no longer, people no longer are using rule-based systems there. Most efficient voice recognition systems are machine learning based, whereby rules are created by the computer, not by the people. All right? Rules are created by the computer, not by the people. So the voice recognition is essentially the, as of now, it is based on the deep learning. Earlier, it was based on the machine learning, classic machine learning. Before that, it was based on normal signal processing and hand-coded rules. And the whole thing is AI. It doesn't matter whether you were using rules, you were using the voice processing, you were using statistics, you were using the neural network. It doesn't matter as long as it's able to behave like human, that is recognizing the voice. All right. At the end of it, we are meeting the AI under the hood. Unless we take a look at the model, we can't really predict whether it's machine learning or deep learning, but probability is that it's going to be deep learning is designed today. All right. Driverless car comes under which technique? Driverless car is basically an example of AI. Basically, it's an artificial driver, okay, which behave like human to drive a car. So it's an AI, but it has many components. A component which processes the visuals, a component which processes the sound, a component which decides based on the predefined rules, and so on. So a driverless car had some part based on machine learning, some part deep learning, some part hand-coded, some part are based on simple statistic techniques. So driverless car, though, is an example of AI, but the various component of it fall under machine learning, deep learning, or classic programming. All right. A question is how driverless cars are operated. I hope I was able to answer that question. That driverless car, basically there is a convolution neural network or computer vision algorithms looking at the photo, identifying the boundaries of various objects, and then taking a decision based on that. Also, it's learning in the real time, which is in some cases it's learning from the real time. That's called the reinforcement learning. A question is, which is most promising research topic in image processing currently? The research topic in case of image processing are many more. There are current, just take a look at the trending ones. There is a tremendous amount of work happening cleaning the image, creating the image, creating even the same technique of computer vision are also being used in the voice, are also being used in the language processing. So take a look at the recent paper. The computer vision has got tremendous scope, specifically creational computer vision techniques like the GAN has got a tremendous traction. But trust me, any branch you pick from the computer vision, it's any idea you pick, it's going to be great. It's going to be great. And if you are planning to pick up a project, we are also trying to launch a couple of projects under Deja Vu. What we are trying to do is we're trying to do the real-time face recognition of people and giving it as SDK so that people who are building the mobile app, they can use our SDK and then can utilize that to recognize and do various kinds of tasks. Okay, so it's a amazing field, and any topic you pick has got decent depth. Okay, a question is, what is reinforcement learning? Reinforcement learning is what human does. They walk in an environment, learn from the environment, and then apply those learning in the same environment. What Mario was doing, or how Mario was being played by the computer, that is an example of reinforcement learning. A question is, that is NLP part of DL subset of AI? Yeah. So again, NLP is a general, just like computer vision. Computer vision is a general topic. Before, say 2009 or 10, computer vision techniques were all rule-based, and therefore all of those were kind of not machine learning, but they were AI. Okay. Similarly, NLP, earlier it was rule-based, whereby people coded the rules, that this is called subject. NLP is natural language processing, in which we have to, given a sentence, we have to infer its meaning. So earlier it was based on grammar, that this is called subject, this is called participle, and participle has a verb, and so on and so forth. That was rule-based. People coded it. Later on, as of today, understanding of the words has become so powerful thanks to the deep neural network that the computer understands the meaning of a frog, and it understands that frog and toad are similar thing. And it learned, how the neural network, we call that word embedding, the way face embedding results are here. Similarly, there's something called word embedding, whereby it converts the word into a vector or an array of numbers, whereby it knows that the frog and the toad are the similar things. Similarly, if you ask it that what it means by king minus man plus woman, king minus man plus woman is queen, right? And the computer is able to do this. So NLP, as of today, it's just amazing field today. Almost every hard problem that human could not figure out looking at the data, today, thanks to those knobs, thanks to the tweaking of the knobs, we are able to figure out the meaning, to figure out the relationship between input and output by tweaking the knobs. A question from Ankit is, I want to classes be online or offline recorded session. Is there any discount available? Okay, please come over to CloudxLab, reach out to us at Reachers. Probably my team can better answer this question. All right. Right now, what we have done is we have done something crazy at CloudxLab. We dropped our prices by crazy amounts. What we want is, we want to give the content at very low cost. We want to give users more and more access to the lab. Okay, and we wanted to, bring it down, and we are even giving the EICT certificate at such a low price. From the business point of view, it did not make sense to give it at a low price, but we realized that it's important for everyone to learn, and it's very, very high time that the the engineers learn machine learning and big data, because that's like heart of everything. A question is, if I want to switch to AI ML related job role, should I go for MTech in AI or ML, or just take up some course? Will the course be enough? So if you are a freshman, probably going for MTech would make sense. But what I suggest is that whether you do MTech or PhD, you're going to learn by yourself. Probably take up any course online like this. Okay. So the important part is, if you have experience, people wouldn't really ask you about your degree. Instead, they will ask you about what you have done um, as a programming, as a computing, or as a management, product management, and so on. And then they will see that, okay, you have learned all of these, and so on. But like for me, I haven't done, for example, I haven't done masters, but most of my learners have done PhDs and masters already. And I can assure you that lots of people approach me with respect to, how their problem can be solved and so on. So if you are knowledgeable about the field, if you can answer the interview, you don't really need a postgraduate degree. Okay. And second is that even if you go for postgraduate degree, these things you'll have to learn by yourself. Okay. We make artificial eye for blind people instantaneously using camera, using deep learning. Do we have real-time fast computing controller or processor? Suppose it's available. Kali said, good question. Good question. If you are interested, I can guide you and mentor your project. All right. If you're interested and really serious about it, I can mentor you in this. It is very much possible today, and given the current state, but given the current state, you can actually do it almost real time. Okay, given the fact that the example that we took, like YOLO, was amazing because that one can do 60 frames per second on a GPU, and a GPU, not like really high-end GPU, just like a low-end 4 GB GPU, really, really fast. Therefore, it is very much possible to do it real time. Okay, so if you are interested, just let us know. A question from Santosh: what is SVM? What type of learning? It's basically a mathematical way of learning. It's called support vector machine. Just take a look at one of my chapters in the course, either on the YouTube or on our platform. I've given like say 6 hours of details in the SVM. SVM was really hot a few years back before the deep learning came into play, but now everything has been eaten up by the neural networks. Okay, a question from Nokia is that how can MI help in, how can ML help in solving Okay. Okay, so the way we solve most of the NP hard problems like traveling salesman is by heuristics and as well as greedy algorithms, right? So the only problem with the greedy algorithms is that they are hardly, they go for the first optimal solution rather than all, right? So those kind of problems can be solved with machine learning, but I'm not sure about the answer. My suggestion will be that give it a shot, observe how well the neural network works, and then you'll be able to figure out how to tweak and make it better, right? Like for example, somebody was trying to solve the Rubik's cube using the neural network, and but again, it ended up being rule based. Question is it beneficial to use ML in such cases, or a supercomputer remains a better option? So there is no hard and fast rule. The only thing is that when you are looking for exact solution, okay, then probably you should go with your rule-based or your own algorithm. But if you're looking for approximation where you are not able to code it so well and you want to learn from the data, you have the data, then let machine learning decide. Say, for example, I was trying to calculate 1 by root x using deep learning, and it gave good result, but not as good as 1 by root x normally. A question is computer vision image versus image processing. Computer vision is nothing but basically a big term for all kinds of image processing. So computer vision has everything in it, like image processing, video processing, and so on, right? Recognizing people in the images, uh, dogs in the images, and so on. It has everything. So image processing is just one part of the computer vision. How can ML help in document review work where we can approve, disapprove document based on certain guidelines by looking through documents? Wonderful question, wonderful question. So you can actually build multiple kinds of models around it. And yes, it can be very effective. So let's say if you have a historical data of the documents that got approved and that got disapproved, you can combine that. You can convert the whole document into a set of numbers, and you can feed that to algorithm to learn from that document. All right, just like you have spam and spam not spam kind of filters. Similarly, you can build your own system, just that you need to have the history of approved and disapproved documents. All right. Question is how much auto ML is effective. Auto ML is very effective. It has taken a lot of pain out of people's life. But my suggestion will be that understand the problem, translate the problem into the parameters to be fed to the neural network. That is something you anyway have to do whether you are using auto ML or not using auto ML. Okay, auto ML is effective because it takes away a lot of chores, but at the same time, problem solving will have to be done by you. From Roshan is, I made row sign detection recognition system using MATLAB and Simulink. How can I detect road sign using Python? If you have images of that one, you can just actually train any neural network, maybe a simple one, and then get it started. Okay, there are a lot of quite a few projects. You should take a look at our course, whereby I have shown how to do all of these using the deep learning. Okay, question from SJ is, does the deep learning course use a TensorFlow? So there we are using TensorFlow 1, but later point of time, we have shown how to use TensorFlow 2. Good part is that what can be done in TensorFlow 2 can be done with TensorFlow 1. I wanted to specifically emphasize on the utility of the way things were done in TensorFlow 1. So most of the course is in TensorFlow 1, but wherever needed in the beginning itself, we have given examples on how to use TensorFlow 2. All right. So you will be able to deal with both TensorFlow 1 and 2. Because in many cases, what I found when I was doing a couple of very practical examples, specifically the one that I was doing with IT Bombay, there what I realized is that the normal TensorFlow 2 models were not that flexible. They were just assuming that all you need to do is change the number of layers, number of neurons, and so on. But when I did the real work, I realized that I need to change the objective function and everything. Okay, and yes, AutoML couldn't have there. Okay, so there I realized that TensorFlow 1 was way more, better. For efficiency, you can use the TensorFlow 2 kind of API. For flexibility, you will anyway have to get down to TensorFlow 1 from time to time. So have a great day. Thank you, everyone. Wonderful set of questions. And I'm really happy that you've taken 2.5 hours of your time from your very important hours of your time, and went through this session. I hope it was valuable to you. I hope you learned something new today. I hope this would help in your career, and this would also give you a bit of direction in your life. All right. So feel free to reach out to me if you have any questions. You can come over to the LinkedIn. My name is Sandeep Giri, and you can recognize me from this photo. And all right, so that's pretty much. And yeah, I'm a real person here. Hi. So thank you, everyone. Thank you for joining in this session. And I look forward to see you over the LinkedIn or on the CloudxLab. Feel free to join me. And I did not want to keep the session theoretical. I wanted it to be substantial so that it can cater to everyone. Because the audience here is there, I mean, from all across the globe. So everybody, I mean, with keeping the respect for the time, it's very important for it to be substantial. So I hope that you got the idea on what is machine learning, what's computer vision, what's AI, deep learning, understood how does the machine learn, the gradient descent, and also brief of backpropagation and what it means by face recognition and so on.